Hello, and thanks for joining us in this new episode. Today, we're diving into a fascinating topic in electromagnetics, the calculation of mutual inductance between a circular loop and filaments of any arbitrary shape.
Yeah, it's a bit of a mouthful, but it's actually really important. Mutual inductance is basically how two electrical conductors influence each other magnetically when current flows through them.
Right, and to put it simply, you can think of mutual inductance as a kind of magnetic handshake between two loops of wire. The stronger the handshake, the more they affect each other.
I like that. A magnetic handshake. And this concept is at the heart of so many technologies we use every day. Wireless charging, sensors, electromagnetic levitation, even some medical devices.
Exactly. But here's the catch. While calculating mutual inductance between simple shapes like two circles is pretty well understood, real-world devices often have coils or filaments shaped in all sorts of complex ways. Spirals, helices, arcs, or irregular polygons, and they can be positioned anywhere in three-dimensional space.
And that makes the calculation a lot trickier. Most existing formulas only cover simple or very specific arrangements. So engineers and scientists have been looking for better ways to handle these arbitrary shapes and positions.
That's where this new research comes in. The authors developed two new analytical formulas to calculate the mutual inductance between a circular filament and a single-line segment positioned anywhere in space.
Two formulas, you say? What are they called?
One is called the Mutual Inductance Method, or MIM, and the other is Babic's method, or BM. Both use integral expressions involving elliptic functions, which are special mathematical functions often used in electromagnetic theory.
Elliptic functions. Those sound complicated.
They are a bit, but the key insight here is that any complex curve can be approximated by a series of straight line segments. So instead of trying to calculate mutual inductance for a complicated shape directly, you break it down into many small line segments.
Like approximating a curve with lots of tiny straight lines. The more lines you use, the closer you get to the real shape.
Exactly. This is called the segmentation method. You calculate the mutual inductance between the circular filament and each line segment using those formulas, then sum them all up to get the total mutual inductance for the entire shape.
That's clever. So the only input you need is a set of points along the filament, which define those line segments.
Yes, and this method is very flexible. It can handle all sorts of shapes: circles, arcs, ellipses, spirals, helices, conical helices, and even polygons like squares or triangles.
And I imagine this is really useful for engineers designing coils for wireless power transfer or sensors, where the shapes can be quite complex.
Absolutely. Now, the researchers didn't just propose this method, they validated it thoroughly. They compared their results with FastHenry, which is a well-known software for inductance calculations, and also with reference examples from the literature.
And how did it hold up?
Very well. The results showed excellent agreement, confirming the accuracy of both the formulas and the segmentation method.
That's reassuring. But I guess the accuracy depends on how many line segments you use to approximate the curve.
Exactly. The more segments, the better the approximation and the higher the accuracy. They found that to get a relative error less than about 0.1%, you typically need more than 100 line segments.
Makes sense. It's like drawing a circle with straight lines. The more lines, the smoother it looks.
Right. And an interesting technical advantage is that this segmentation method avoids singularities, those pesky mathematical problems that can happen in other methods when filaments are perpendicular.
Oh, that's neat. So it's more robust in tricky cases.
Yes, and they also observed a kind of chaotic but very small error distribution in some cases, but it's negligible for practical purposes.
So what kind of examples did they test this on?
They looked at mutual inductance between a circular filament and polygons like squares, triangles, and hexagons, positioned arbitrarily in space. They also tested spirals and helices, which are common in wireless power coils and sensors.
And elliptic arcs and ellipses too, right? That really shows the flexibility of the method.
Exactly. Basically, any shape that can be represented as a curve in three-dimensional space can be handled.
That's powerful. And the real-world impact is significant. Wireless power transfer systems, electromagnetic levitation, biomedical devices, micromachine contactless suspensions, even nuclear magnetic resonance and indoor positioning systems.
Yes, and the method can be extended beyond just mutual inductance. It can help calculate magnetic forces, stiffness, and magnetic flux density gradients between arbitrary filaments.
So this opens doors for better design and optimization of all kinds of electromagnetic systems.
Definitely. To sum up, the researchers developed two new formulas and a segmentation method that together allow accurate calculation of mutual inductance between a circular filament and any arbitrarily shaped filament in any position.
It's a great example of breaking down a complex problem into simpler parts. Here, line segments, to unlock practical solutions in engineering.
Well said. And the fact that it's validated and flexible makes it a valuable tool for engineers and scientists working with electromagnetic systems.
Thanks for exploring this with me. It's always fascinating to see how math and physics come together to solve real-world challenges.
Absolutely. Thanks for listening, and we'll catch you next time.